Good afternoon, everyone. So welcome to the LHC virtual tour. So what we plan to do today is we will start with the relatively short introduction about the subject of particle physics. We'll tell you what we're doing, why, how it all started, a little bit of history, what kind of questions we're trying to answer. And after that, we will switch to our colleagues at CERN in Switzerland at the site of the compact Muon solenoid experiment, which is the experiment that the group from Texas A&M is participating in. And they will walk us through what's happening on that side, and then we'll set some time aside for questions. Yes, please. That's a good question. Yeah, maybe we can just dial it a little bit down. Is it better? Kind of, yeah. Maybe a little more. I think it's pretty loud. Can people hear me? And it's better, yeah? Okay, wonderful. All right, so let me start with a little bit of an introduction. I should tell you who I am. My name is Alexei Safonov. I'm a professor here, and I lead the CMS group at Texas A&M. We're a pretty large group, so we have 4 faculty, engineers, we have postdoctoral researchers, graduate students, 2 of whom are here. They will introduce themselves a little later. Part of our group is actually stationed in Switzerland. So they work on the experiment side, and so they will help with the tour from that side. So the subject of particle physics, and that's what we call ourselves. We call ourselves particle physics physicists. Starts kind of like with what do we know about matter, right, surrounding us? What is everything built around us? What is the universe built of? And we actually know quite a bit, right? So we know that everything around us is built of molecules, right? Molecules, in turn, are made of atoms. Atoms, the simplest one will be the hydrogen atom, right? Has a proton and has an electron flying around it. What keeps atoms together inside molecules, we also know these are basically electrons, because there are electrical charges, some of them electrons are negative, nuclei are positive, and everything holds together. And then you can come up with various ways to combine different elements together, and you end up with different molecules. Could be some are very simple, some could be very complex. If you look at how long we know this, actually not that long. So it's about maybe 100 years since all this knowledge came to the coherent point of knowing it. So of course, as all sciences, everything started with ancient Greeks. And it started with philosophers, right? So they know everything. So that's basically where, when I said atom, so the term atom does come from ancient Greece, and the first completely incorrect model of atom came from ancient Greece. So but then if we fast forward to 20th century, we got to the point where we know how an atom works. Quantum mechanics, which surrounds us everywhere, right? Your cell phones, television, whatever, all relies on the principle of quantum mechanics, helped explain how atoms can hold together. So if you look at the atom, right, there is a nuclei and then there are electrons flying around. How come electrons don't just fall on a nuclei? Because they should be emitting radiation, should run out of energy and just fall. Quantum mechanics explained why that does not happen and how this thing survives. Was a major breakthrough, lots of predictions, experimentally confirmed. Now, what we have around us, as I said before, largely relies on principles of quantum mechanics. But you can step forward and ask, well, it's great, but inside of this nuclei, you have protons and neutrons. Protons are positively charged, they should repel. How come everything is not falling apart? So that's how the science of nuclear physics has started. So the previous stuff we call atomic and molecular physics. If you go a little bit deeper, that's nuclear physics. Nuclear physics studies what happens inside the nuclei. And they proposed a new particle at that time, like it was like beginning of 20th century, called a pion. And the idea was that this pion will somehow attract protons and balance these electric forces that are trying to pull the whole thing apart. And everything was good for a little bit, but then we found that pion is decaying. And it decays to a muon, and mu meson, it's kind of like heavier cousin of an electron. And they're flying all the time from space, like so if you just stand and look up, you have several muons flying through you like every second. And so there was a problem. It was clear that we need to go further beyond nuclear physics. You need to look what's inside the pion or maybe proton. And how do you do that? Well, if you want to look inside something, it's easy, right? Kids know that. Break it. How do you break it, though, right? We're talking about something you cannot possibly see, right? It's so microscopic that, there's no way to see it. You can't see them, but you can control them. So for example, if you have some protons, you can use electric field to direct them in a certain direction. And then, if you work out the technologies, you may be able to take a bunch of protons, accelerate them in one direction, take another bunch of protons, accelerate them in the other direction, and maybe collide them somewhere. And you just invented the accelerator. So what accelerators do is exactly that. You take particles, accelerate them to very high energies, and collide them. And then, the idea would be you break them, see what comes out of it. Maybe you will learn something about what's inside. But there is more. So the Einstein special relativity says that you can take energy and convert it into mass. So if you have enough energy, maybe you can produce something new, some new types of particles that you could not ordinarily see. And that basically is particle physics. The second you start talking about what's inside the proton, how things are holding together inside the proton, that's particle physics. And particle colliders, there's been several dozen different particle colliders in the 20th century that basically defined everything we know about particles. We found new so-called heavy quarks. So like the light quarks is what the protons consist of. Everything else normally does not exist around us, but it did exist at the time when the universe has started. And then things started decaying into light stuff, but we were able to reproduce them again. So these particle colliders found a gazillion different particles. I brought this book. We don't print them anymore. They're all digital. But this is basically a listing of different particles discovered by colliders in the 20th century. Most of them are composite particles, so only few are fundamental. And from this fundamental, you can use them as building blocks to build these composite particles. And everything was great, but we still did not have the Higgs boson. And the Higgs boson is in the heart of the whole thing. It gives masses to all other particles. If it does not exist, all our theoretical contraptions here just make no sense. Just cannot work like that. And I already alluded to that, but particle physics is very closely connected with our studies of the universe and its history and its evolution. Whereas in the very beginning of the universe, you had basically a very large amount of energy in a very, very small amount of space. And then that energy started creating space around itself. So the space was not there. Somebody needs to create space. So that energy created space around it, creating the universe. The universe was expanding. Heavy particles were decaying to light particles. And effectively what we're trying to do with the particle accelerators, we're trying to go back in time. We want to go to conditions in early universe and see how things were happening. I already told you about the Higgs boson that, as you, I'm sure, know, it has been discovered about 10 years ago, well, almost 15 years ago at the Large Hadron Collider. But Texas actually was this close to discovering the Higgs boson before the Europeans. And so if, some of us are old enough to remember that there was a plan to build the super collider not too far from Dallas. So it eventually got closed, and so there is only pictures left of what that looks like. But eventually, Higgs boson was discovered with the Large Hadron Collider, which is right now the highest energy accelerator in the world. It's in Switzerland, near Geneva. So it's a big underground tunnel. I will let my colleagues on the other side tell you more about this, but like this is an enormous, large scientific instrument, incredibly complex, so Higgs discovery was a very, very essential part to what we know now about particle physics. Books literally had to be rewritten since the discovery of the Higgs boson. We keep working on this, right? We discovered Higgs. You could say, well, good, go home. No, there is much more to do. And so to give you some examples of what we're trying to understand and why it's important, I'll give you just three. So one is the dark matter. So like we know that visible normal matter, that atoms, that we are built of, that everything around us is built of, explains only 4% of the total energy of the universe. Roughly 5-6 times more is the so-called dark matter. We know it exists because we see it in various astronomical and astrophysical observations. We have no clue what that is. So like maybe it's like some other type of particles, like who knows. But basically we don't. And one goal of the Large Hadron Collider, maybe we can produce these dark matter particles and then we can see them and then we can explain it. Another thing is the evolution of the universe. We kind of know quite a bit about how the universe was evolving from the beginning to today. What's going to happen next? Good question, right? So like actually, if you look at our current theoretical understanding, if everything that we have is just exactly correct and exactly like we think, our universe is actually not stable. It's metastable. And there is a very, very small probability that, I don't know, just like this, the whole thing can kind of freeze. And, the laws of gravity, laws of electric magnetism, everything will stop working. The world will cease existing. All of us will cease existing. The good news, the lifetime or half-lifetime of such potential transition that could lead to this disaster is much bigger than the life of universe. So like, probabilistically speaking, it can happen, but it's not very likely. Another example is the matter-antimatter symmetry. We know experimentally that everything around us is built of protons and electrons. If you think that the universe has started like as one hot piece of energy, then for each proton, there should be antiproton. For each electron, should be anti-electron called positron. Didn't happen. And there must be some fundamental explanation behind it, why we are having matter and what happened to all the antimatter. And so these are just some examples of what we're studying at LHC. And, I'm done with my small introduction. And so now we will go to our colleagues at CERN. And they will take over from here. So let me zoom this thing in. By the way, can people see this pretty well? What we can try doing, I'm a little worried about too many pole lights, but is this okay?
Yeah.
Okay.
Let us know when you're ready.
All right, Mohammed, so to you guys.
Yeah. Okay. Hi, everyone. Let's start with a quick introduction. My name is Muhammad Ahmad. I'm a postdoc at Texas A&M University. I work for CMS Experiment, as Alexei introduced. So I'm one of the group members who work on CMS Experiment. and I have a colleague of mine with me who will also help with the visit today. So what I work on CSE. It's one of the Muon detector. So I work on the operations for recording good quality data, and also at the same time I work on Higgs properties measurement. So here's
so I'm Derek Grove. I'm not from Texas, but I'm from University of Kansas. So I'm also from the US, and I'm currently based here. And yeah, sorry, but
yeah. So
two Midwest schools, and then we work together on CMS. I'm a PhD student, whereas Ahmad's a postdoc. And yeah, we're excited to show you our experiment here today.
So how I would organize, I would quickly tell you a little bit about the area where we are, and then in the meantime, my colleague will prepare to go underground and also show you the things in the control room. So as Alexei quickly introduced, but I'll like to say a few more words about this. So this is the Large Hadron Collider, what you see, the yellow tunnel. It's 27-kilometer circumference. We have 4 experiments installed on this large collider. The one we are sitting now is here. You can see with the arrow CMS, compact Muon solenoid. And then there are other 3 experiments, LS, Atlas, LHCb. Here is the CERN main site. Somewhere here, you can see the Geneva Lake, and then close to LHCb, you see the Geneva airport. So this is the area. So at CMS, we also call it sometime 0.5. How this is named, there are points where you can actually get into the tunnel, and they are simply named as 0.1, 0.2, 0.3, and they are 8 in total on the circle. So at this moment, we are at 0.5, where CMS, one of these 4 detector, is installed. We are taking data nowadays, so we won't have access to see the real detector, but we will still go underground, see some of the technology, the boards. We'll also show at least few of the things where Texas A&M is involved, and also show you the control room. So
we can show you.
We muted. So can you mute? Thank you. Sorry, we're running the technology here, but so we are in the control room, as you can see, and there's our virtual visit setup there. But as we pan around the room, you'll get a sense of, how many people, although it's the weekend and it's at night here, but normally there's a person at every single one of these stations 24/7, and they're monitoring the detector and making sure everything's running. And there's also a ton of people at home that are on call. So that's why you don't see them all here. But they're also responsible for running everything. And if we look at, I guess we come back over here to where we were, but we would like to show you, so we have stable beams right now. And if we look, these are some live event displays where you can see some of these collisions and the particles that are coming out of them. And so now I think we will make our way underground. And while we're moving, though, we can give it back to Mohammed to talk more about our experiment.
Okay. Are we projecting this? Can we? Oh, yeah. Thank you. Yeah. So a few words about this whole accelerator complex. So as Alexei introduced, that we collide protons in this big accelerator, but we start simply from linear accelerator. You can see here LINAC 2, LINAC 3, and then we use electric and magnetic field. So electric use field to accelerate them, and magnetic to bend the beam in these tunnels, and we want to accelerate these electrons almost close to the speed of light. Okay, so now my colleague is trying to get into this door, so I'll.
Sorry, I will give you back later.
Yeah. So.
Hello. So we're about to go through this big door to get to the underground area, to get to the elevator that takes us underground. But there's a lot of safety procedures here at CERN and also at our experiment CMS, where you need to carry this, a personal dosimeter. So it has my name on it. And then there's also this RFID sensor in it. It says it's mine, but it is also linked to my biometrics. So like a scan of my retina. So this is all to make sure that if anybody stole my dosimeter, they wouldn't be able to like sneak in to these areas where there could be some radiation or get into some trouble. So how this works is I will scan this ID, this dosimeter. It will let me into this little room, shut both the doors, scan my body to make sure nobody's, sneaking in with me. But then I have to look into that black box, which will scan my eyeball, my retina, both of them, yeah, and make sure it matches. And then only after all of that works will it let me through that next door to the underground area. So we will now show you this in action. And then, of course, Naomi, our camera guide, will have to do the same. So I'm in here. Let's see. And sometimes it fails because it's that body scan. It wants to make sure that you don't take anything in with you. Yeah, or somebody else. That's a bit funny because she has to smuggle the camera in. So I think if I stand this way, yeah. And then I can turn and I stare into the box. And it says, thank you, I've been identified. So now she will bring you through and you'll get to see what this looks like. But any of the underground areas at CERN, at any of the experiments, all the engineers, all the physicists, we all have to do this procedure. And there she's successfully smuggled the camera and the tripod, but that's okay. It's allowed for these. All right, so now we're good to go ahead. We'll catch the elevator and we will lose our internet connection as we're going 100 meters, or since we're talking to people in the US, when we go 300 feet roughly underground. Yeah, we're going to lose our Wi-Fi connection, but we'll try to stay on as long as we can. But of course, while we're doing this, we'll give it back to Mohammed. He can talk some more from the control room.
Okay, so we can finish what we were talking about this big accelerator complex. So we were talking that these protons are injected. So we ionize the hydrogen gas, remove electron. We left with only protons, which are injected here in this LINAC accelerator. Then they move to bigger and bigger tunnels sequentially as they get faster and faster. So they move from booster to PS to SPS and to finally the bigger ring, which is Large Hadron Collider, which is 27 kilometers. So at every time, have two beams clockwise and anti-clockwise, and we let these beam cross each other at 4 of these yellow points, which you can see where each of the experiment is installed. And when these collisions are happening, there are new particles or old particles produced, and they entered in this detector, which gets recorded, and we save all this data to do the physics measurements on this. So that's also another view how this whole area look like. You can see this big giant tunnel. You can see we are here at CMS 0.5 where this big giant CMS detector is installed as compared to others, while in the surrounding you can see the Lake of Geneva and then the mountains in this area. You can also see this dotted white line, which is Swiss and French border. So CERN has infrastructure in both sides. So at this point, CMS is actually close to a French village, Sassy. So that's how the pictures of detector look like. We are at CMS. Both CMS and Atlas are those detectors which discovered Higgs boson in 2012. They both are competing with each other, different technology, but working at the same time, sitting in opposite each other in the tunnel, cross-checking also, while other two are very dedicated. So LS is very specialized detector to do heavy ion physics. They study mostly quark gluon plasma, while LHCb is what Alexei was described, this matter-antimatter asymmetry. So this detector is very specialized to study that kind of physics. This is the area which we would be visiting. So we have these two tunnels which you can see, two underground areas, PM54 and the other one. So one of this is not accessible. This one where exactly the detector is installed, we have a huge concrete wall between these two areas, which stops all the radiation. So people still go to PM55 and our colleague is there at this moment, and he will show us the electronics and things in the service area. So
Okay, hello from 300 meters, 300 feet underground. You want to see what's in here, right? Sorry. So we had to mess with our internet for a bit, but now that we're connected. So we'll first try to show you from where we came from all the way up at the surface. We're down this hole, and you can just barely, maybe not with the camera, see the top, but what you're looking at is those are all the flights of stairs that you would have to take if you wanted to walk down here. And in the event of an emergency, we do not use the stairs. They are there for some sort of extreme emergency. But the elevator is actually used in the event of a fire or a gas leak because it has its own power supply. It has its own oxygen supply. These stairs are not what you would use in an emergency. They're really there for the fire department if they really, really needed them. But yeah, so we are quite far underground. Those lights are just to demonstrate that, you know, we send the data back to the surface. It's just for fun. But yeah, so we're going to go into this next room. We call it the counting room. I also like to think of it as like the brain of CMS. It has all of the electronics that are associated with well, counting and doing a large part of this decision making about the data coming out of the CMS detector. So we were requested to go down this aisle first and look for, oh, it's right here.
yeah,
These boards, yes, perfect. Oh, you're right, they are right here.
You can open this
Yes.
and take one of this red board out.
These are spare boards on.
So
Yeah, they
I
are
was given permission to do this by Muhammad, but this board here, as you can see, has the ANM logo on it. And so, Muhammad, you could mention something about this board. You know more about it than me.
Yeah, so as Alexei described, we have a large group who work on CMS. We also work on GEMS, we work on CSC. So this is one of the board which was where we were sitting. So this board was sitting there. It's a trigger board connected to CSC chambers. So we just want to show you one of the area where Texas A&M is involved. Of course, there are more, and we'll see also some of the more area, and I'll mention as we go.
I want to make sure I put it back right. There we go. So, yeah, this room is full of, you can see there's other boards, of course, from, yeah, they're all spares. None of them are, you know, on or powered right now. But we'll go through the rest of this room now and look at some of the other electronics in here. So a lot of the racks in here, well, I actually don't know what these racks are. It's labeled detector safety. I believe that's what it's for. I'm more familiar with what's over in the pixel racks. So let's go right there. But these racks are related to the trigger. And so the trigger is part of the decision-making process. What collision events are good events, as in which ones do we want to save and record to our hard disk drives. Unfortunately, we cannot save all of the collisions. There's too many, and not all of them are good, so we discard a large majority of them. But we save as many as we can, and these electronics are part of that brain or part of that decision making. But as you can see, like, there is a lot and a lot going on in these racks. There's a lot of pretty nice cable management and not so nice cable management. But for the most part, we're doing a pretty good job. And then we can go down here. I'll show off these ones, but I work a lot with the Pixel, which is the innermost part of CMS. And so these boards, these are labeled Pixel Feds. And so these are responsible for getting some of the information, the first information basically out of the pixel detectors, and then doing some logic with it, but then also sending it off to the next part of the data readout chain. So when you see these cyan cables that are here, those are actually optical fibers. And those are what are coming from inside the experimental cavern. And so we use optical for a couple reasons. One, it's very fast, but also two, it's unaffected by the very strong magnetic fields that we have from our experiment. So yeah, we can now also do a little test here. Since we're so close to CMS, we should be in its magnetic field. It's just on the other side of this wall. And so if I hold something magnetic, we can kind of see that, yes, it's actually a strong enough field to affect these paper clips here. And it also can kind of show you the direction, because even if I try to rotate it, they stay aligned with the field. So if I take it near something magnetic, it'll jump to it. But yeah, we'll see a little bit more of this as we get right up to the door that would go into CMS. But yeah, also I'll point out there's a lot of these hatches to let you underground, because there's going to be, I can open it, yeah. I won't go down, no. But there's even more stuff underneath this floor that other people have to access to do their maintenance or their service work. And so I remember one time I was working on these feds with my colleagues, and we also had a group of people literally right underneath us. And, you know, we were working here, and they would like knock on the floor, and we'd have to let them up and then shut the hatch. And it was this whole thing. But this is what it's like to, yeah, kind of work in this environment, work on this experiment. There is a lot going on. And also no one person knows everything. It's important to keep that in mind. We have many, many people here from around the world. Mohammed and I, yeah, we're here from representing US institutions, but we learn what we have to about our one little thing and then contribute. So under here, we see even more cables. And I was told these red cables are the high voltage to the Muon systems, or just to GEMS. Yeah. But a lot of the detectors require very high voltage in order to be in this state where they can detect particles. To give you an analogy for why they need a high voltage, you can imagine if you built like a tower of cards. It only takes one little gust to come in and knock down the whole tower. So when you apply this high voltage to the detectors, you have a very high voltage, but it hasn't broken down, or it hasn't sparked, or it hasn't pulsed. It waits for, or it needs a particle to come through and kind of, you know, knock that voltage into this big pulse that then we read out. And that's how you detect a particle, at least in those systems. We're kind of, we're doing good on time, but we'll show you this door actually leads directly to the tunnel where the Large Hadron Collider is, you know, the big 27-kilometer ring. I try to convert to miles, but I won't So right through this door is where the beam is, the beam pipe. If we were to go in there, it would dump the beam. Since we have the beam right now, you cannot go in there. There is some background radiation and it's, generally not safe. So if you were to go through this door, it would immediately dump the beam. There's a giant piece of granite that we shoot the beam into when we need to get rid of it. It would dump the beam before, I imagine, before you could even get the door open. And then, of course, that would be a very expensive mistake. Yes. So this is asking you to please not use this door unless it is an emergency. There's emergency exits on the other side. If there was a gas leak or a fire, say over there where we just came through, then Naomi and we would go through here to escape. That would be the right thing to do. But because it dumps the beam, that can be quite expensive, so you don't want to do that by accident. This is what it would look like if we could go in there. This is a very nice picture of the tunnel, and you can see the big beam pipe, basically. And it's a bit misleading, but this the size of this thing is really because of the cooling. So we have these superconducting magnets, which actually we can see in this picture here. So of the big, blue tube, really the beam is only this very tiny, the beam pipes are these very tiny pipes in the middle, and they carry one beam going this way and another beam going the other way. And then of course we crisscross them in the middle of the detector. That's how we do the collisions. But these are quite small compared to the whole thing. And it's because we have these superconducting magnets that are used to focus and steer the beam and keep it, in the beam pipe. And those, since they're superconducting, they need to be at minus 270 degrees Celsius, which is basically, it's only a degree or two above absolute zero. And we keep it that cold with liquid helium. And so this whole thing is really just almost like thermal insulation, you can imagine. And it's to really keep that as cold as possible to keep control of the beam. Here's another nice image, maybe from a different perspective. If you could look inside the beam pipe, you would see this. And the superconducting magnets are these kind of pieces here on the edge of the beam pipes. So yeah, I don't know if there's anything you want to add from the control room, but we're almost finished down here. We're going to show the grand finale, but chime in if you want to.
Yeah.
So go ahead.
Yeah, you can show this last door if you have anything to talk about this, and then we'll take
Okay.
questions also. I mean,
Yeah.
very hard to cover everything in this 1
Yes,
hour.
exactly.
And then
And we're keeping track of time. So once we're kind of finished here, we'll rush up and also join for questions. But yeah, we'll get through this. So this is the door that leads into the experimental cavern, or where the detector is. And so if you're very interested, we have many other videos where we did virtual tours. Even I did some where we got to go in here. And that was, when we weren't running the collisions, so there wasn't this excessive radiation that, was preventing us from going in. So if you want to, you can go look that up. But, we can't go in now, but this is what it looks like. It's a similar system as above, where you need to scan a dosimeter and it needs to scan your eyeballs. But there's an additional safety feature, which is these actually swing open for a very short time. You have a short time window where you have to reach in and take a key. And every person that goes in has to take a key with them. It won't let you in unless you have a key. And then when you come out, you must return the key. And that's a very effective way of additionally counting. If you have 3 people go in, 3 keys must be returned. If 3 keys are not returned, then CERN, the control room for the Large Hadron Collider, they cannot turn on the beam at all. So every experiment has this system, as far as I know, with the keys. And yeah, if anybody were to forget to return a key, which I heard a story there was one time, they can't turn on the beam, and it's a big deal. But that's how, that's how serious we take the safety here. Okay, so the last thing I want to show you, although we can't go in, I said we're very close to the detector, so we are within its magnetic field. So I brought a bunch of paper clips with me, and they're not connected or anything, but they're already like kind of sticking together. So I like to just kind of throw them around, and we see that because of the field, they're sticking together, they're magnetized. Some of them are even standing up, you know, on their own. But yeah, they do all sorts of crazy things. It makes cleanup a bit easier since they all stick together. And then you can also build, you know, a chain of a few of them like this. So it's a bit of a freaky thing when you're here in person, and you know, a person or a human, you know, we're organic. We're made out of like carbon and nitrogen and oxygen. So we really don't feel this. We don't feel it at all. But clearly these magnetic materials do. And so I can bring this up here and even build, I'll get some more, but build this paperclip chain with these magnetic paper clips. So, and it's important, the shape, because it actually tells you a little bit about the direction of the magnetic field here. If you have seen other physics demonstrations with magnetic fields, the shape of them can be a little complicated. They kind of like wrap around the thing that is magnetic. And so, yeah, they don't always point in the same direction, but where we are, it's roughly this way, influenced by the other magnetic things here. But yeah, so I'm having a good time. And yeah, you can make a compass. You can like put it on your phone. Well, can you put it on your screen, maybe? But I built a pretty nice chain here. So yeah, we don't feel anything, and it's not harmful to you. If you have a pacemaker, though, that's like an artificial implant that helps keep your heart beating. That would be affected by the field, though. So people that have pacemakers cannot come down here. But we do our best to try to give them virtual tours like this so they can experience it at least somehow. And yeah, we'll pick up this mess and start making our way back to the control room now. Mohammed, if you have anything to add.
Yeah, I'll take 1 more minute and then we should go for questions. I mean,
Sure.
the magnetic field you are saying is only few millitesla. Yeah.
Oh yeah.
And the actual magnetic field inside experiment is 3.8 Tesla, so about a 1,000 factor of higher. We also used to go there with the whole magnetic field on with a special instrument. Of course, you cannot take anything magnetic with you, but it's not harmful for human body.
Indeed, there are no physiological things up to 10 Tesla or 10-ish Tesla.
Yeah.
As you just said, the maximum field inside the detector is something like 3.8, which is comparable to an MRI.
Zoltan, we can barely hear you.
Oh,
Yeah.
sorry. I was just talking about the field strength that you don't feel anything. There is no physiological effects up to 10 Tesla magnetic field somewhere around, and the 3.8 that we have inside the detector, very much buried by the detector structure, is somewhat comparable to a medical MRI machine.
So then the last thing I want to say is kind of advertisement. So from this year, July, we would be going to shut down. So I know this Texas A&M have this annual festival every year. So next 3-year festival, people would have a chance to see the real CMS detector.
More spectacular than today.
Yeah.
Sure.
So the next 3 festival in Texas A&M, we have detector opened for maintenance and upgrade. So just okay, Alexei, yeah, I think we should, it's last 15 minutes, we should people might have
We'll
questions.
start moving to questions, yeah.
And
So
you can also
heard what
help,
he said. So next year, if you want to go see the real CMS experiment, go to Geneva. If you cannot go to Geneva, come back here and we'll show you and we'll give a tour of actual detector. We'll walk around. We'll show you bits and pieces of everything we're working on. So like we are moving now to questions. And so like, so we have two of our group's graduate students, Alex Thornton and Tasifa Akhtar, who will help us navigate the microphones. And so if you have a question, raise your hand and we'll come and yeah, so let's start there.
So how fast does the atom collider move the particles?
If you want to, I mean, it's more than 99.9% of speed of light.
It just plays this.
99.999, many nines.
Yeah, yeah.
Yeah,
So more
you
than
see this.
99.9. You see here, you see this number, this one. As I showed before, like the different tunnels, and as it goes through different sequentially, the speeds tends to increase. And this is the last one, the Large Hadron Collider. So it can never be 100. So we are really reaching up to the limit. So it's 99 point many nines.
Yeah, indeed, what you see here is the circumference of the accelerator.
Yeah.
But we can tell that every proton orbits more than 11,000 times per second
Yeah, in this whole
around
thing.
the accelerator. So
Yeah.
it is pretty fast.
Yeah. So 11,000 times
Per
7
second.
kilometers
Yeah,
per
exactly.
second.
And during each circle, the French-Swiss border twice. Yeah.
Yep. Yep,
So Alex
yep.
was pushing really.
We don't need to pay any taxes.
Mhm.
To operate the collider, what's the power draw or what's the power draw to operate it? Does it affect the city grid when you operate it?
Yes, we buy the electricity from the French provider called EDF, Electricité de France. We are on the normal French network. We get 400 kilowatt inside the CERN complex, and we use something like 200 megawatts if the accelerator is running together all the computers and my desk lamp in my office as well. 200 megawatts is not a big deal.
Yeah.
We don't need any dedicated power plants, any dedicated nuclear reactors. So unlike the urban legends say, we are really part of the normal consumers of the French network.
And we shut down over the winter, right?
Yeah, even though, so this is something, a relic from the past, when the Large Electron Positron Collider was operating here. That time in France, the biggest energy consumption was during winter. Don't forget that they operated their heaters with electricity that time, almost everywhere. Therefore, during Christmas time, during the winter time, we had a bigger energy consumption in France. And since we are not a GDP making institute, of course we could be cut off. We could reduce our consumption.
We
Today-
turn off over the winter, and then
Exactly.
that doesn't stress the grid as much for everybody that's heating their homes. And that
Exactly.
gives us a time to do maintenance.
Exactly. During the lab time, we were off between, let's say, beginning of December and April, and this somehow remained today. Even though today the energy consumption profile in France changed somewhat, we also operate this AC stuff just like in the States.
Okay, well, thank you. So next question. We'll come to you next.
What is the greatest discovery to come out of CERN this far?
If you talk about CMS experiment, I mean, if you talk about CERN, then we have to go one by one back then. If you start from latest, is I would say Higgs boson discovery in 2012. This was the largest one recently from both CMS and Atlas detector. But before LIC, there was also a collider right in the same tunnel the lepton collider where
Large
we
Electron
discovered
Positron Collider.
WZ bosons.
Well, they were discovered in one collider earlier, the superproton synchrotron, in the mid 80s. That created the Nobel Prize, of course. And then the lab was to study the Z boson parameters with a very high precision. Actually,
So
which was the most
Also,
precise.
but to put
equipment
it
that has ever been used.
plainly, you know, throughout our history of doing particle physics, we had kind of these separate theories that actually by now have converged on a single theory. We call it the Standard Model. The Higgs boson was the last greatest domino to fall to kind of prove that this is truly one unified theory of like particle physics. It's not finished though. It doesn't have gravity in it, and there's other problems. But we talk about the Higgs boson a lot. The W and the Z boson was also discovered here at CERN some decades ago.
Mhm.
But it all has unified this.
And it's not only that we discovered particle. I mean,
Mhm.
WWW was first time
Oh yes,
was
Oh,
at
yes.
CERN. That the real purpose was to send data from to distribute the data. And now if you see this WW World Wide Web, it's everywhere, common user.
Yeah.
It's a multi-trillion dollar
We-
industry probably.
But
I
we
can maybe
gave it for
jump in
free.
too on this. So as you can see, it's kind of like in the eyes of the beholder. There were major discoveries, you know, in particle physics. So significant discoveries, you know, like I don't know, like the hydrogen atom was first made at CERN, but for most people living normal lives, World Wide Web started at CERN. I was a undergraduate student, and I think it was 1995 ballpark, and I was at CERN where at that time there was a website that contained links to all websites in the world. Yeah, literally, like maybe in a couple of hours, you could see everything that exists. So you didn't have to do searches, you know, with Google or ask AI to help. Everything was just there. And it was built to exchange data between scientists. And then, of course, you know, like it got commercialized and we have, you know, all of it around us. Yeah.
And also the first non-scientific use of the web is related to CERN as well. People don't know it very well. The first pop band, the LHC, the Laser Reverse Nets, had exactly, and they had the first website which is not scientific related. Actually,
Next question.
You can find their songs on the YouTube.
Yeah.
Yeah.
You only love your collider.
Exactly.
So, another
Okay, let's
question.
go to the next question.
So I know that there's like a bunch of collisions, but what are you kind of like looking for? Like what's the experiment of like dark matter, antimatter, Higgs boson?
It's a really good question. And because we work in the field, like it seems obvious to us what we use it for, but it, you know, the public may not follow it as well. But I guess I would try to describe it. We want to observe these interactions because as you observe more and more interactions, you can start to see maybe some strange things.
At least we hope so.
We hope to see strange things. We have our theory that tells us, oh, this should happen. You should see this happen. You should see this happen half of the time. You know, 2 protons produce some other particle. But then if you start to see like, oh, this only happens maybe 30% of the time, and maybe another fraction of the events, we have a lot of this missing energy. It's invisible. Where's it going? It's producing some sort of invisible particles to our detector. So it's a bit of a hard question to answer because there's many things that we look for in the collision data, but I would say we look for things we don't expect.
So the major question in front of us is still how how our universe is made of, how everything works. So this is the major question, and we go kind of try to hunt for anything.
Exactly.
When you see
Bring
something
it closer to that.
Exactly, and we are pretty sure we know that the story that we call standard model is not complete.
Yeah.
We know, as Derek just told, the gravity is not in there. as Alexei told,
Matter
it is that is the dark matter is something like 5 to 7 times much more than what we have around us, what the standard model tells about. So we know that the universe is a little bit more complex, or much more complex. We want to understand. We want to see how can we observe those non-standard model stuff. One thing what Derek told is the so-called, as we call it, indirect search, when what our model predicts, we can compare to what we see, and this tiny little differences that depend on the statistics very much, since we are using quantum mechanics, that can give us a hint that there is something behind.
Yeah, sometimes it just sends you in a direction, not
Exactly.
exactly just finding something, but setting a direction, like which direction we should look more.
Exactly.
Right, guys, you're already talking to each other. You know, like
Yes, of course.
scientific
Sorry.
question, right? And you'll hear a lecture. So if you don't mind, you know, like we probably have time for just 2 more questions. So let's do that. And please. And we'll come to you next. Okay? You'll be next. Good.
So, I have a question. Since you said that doing like a fire or a gas leak, you will like go through the doors, then what about a earthquake?
That's a good question. First of all, this zone here is not very much prone to happen earthquakes here. What we have is something like a Richter scale 5 in every 1,000 years. Didn't happen since long, indeed. The second thing is that all our equipment has to be able to withstand the Richter scale 3 earthquakes. And the third thing that I want to say, that if anything happens, fortunately, this will have no effect on the GDP.
I actually, personally, I don't know. But like Zoltan said, we built the Large Hadron Collider, the ring, and the experiments on a very big, flat piece of granite all the way down there, with the idea that, well, the engineering understanding that it's very unlikely for an earthquake, or at least a severe earthquake, to happen here. I don't
There
know.
was a long survey that led to picking that specific place to build the collider, because vibrations are bad for this super sensitive things, you know. So, you know,
But
that's
we
a place
are
where earthquakes basically don't happen. Earthquakes. Okay,
Exactly.
so
But,
like we have
but we are
one
sensitive for the
question.
tides. I'm sorry. Go ahead. Yeah. Next question.
How much radiation would you experience if you went into the tunnel when the collider was on?
You cannot go in the tunnel and the collider is on. If this is what Derek showed.
But how much is in there if you did go in?
I don't know the numbers by heart.
Is it a
It
lethal
depends.
dose?
It depends where you are. At the final focus magnets, it's pretty high. That's probably not really healthy. Everywhere else, at the dipoles, you also would be a subject of radiation. But as I said, that we don't play with this. We obey the rules. That the rules say that no living creature when the accelerator is on. Otherwise, the accelerator must be shut down.
So in the experimental cavern, like right now while we're doing stable beams, roughly there is radiation, of course, but let's compare. Is it more or less than, say, like a nuclear reactor? If you were standing.
It's much less than
much less.
reactor.
Okay. So much less radiation than a nuclear reactor, but still an amount that you don't want to be exposed to. So we have all these safety procedures.
Yep. We don't want to play with this. You can imagine that we are a very popular installation here. If anything would happen like this, we would end up on the front pages of the leading newspapers, and definitely we don't want to do this. So that's why we are extremely strict on the safety. Right.
So one more really last question, and then we'll thank our colleagues at CERN.
Hey, I only have one more question, and is that, have dark matter ever talked to y'all?
Alexei, would you like to take this question? It's related to your slides. You say we talk too much, so I give it to you, the last one.
Alexei?
Yeah. No, I haven't talked to dark matter lately.
We're hoping that we know dark matter is a thing, and we expect it to be matter because it interacts with gravity. So gravity is a consequence of having matter somewhere. We see all this extra gravity. We say that extra gravity is from this dark matter we can't see. So we hope that in our collision experiments, we see a new particle, a new something that is a candidate for dark matter. So again, we don't know what dark matter is, but we think that if it is matter, it should be able to be produced in these particle collisions. So
But
that's
how we would see it in the detector?
it would be this.
It would be a missing energy.
Yeah, it's
Right,
invisible.
guys, like we now like really out of time. Before we close, though, I did want to say that we actually have here another collaborator from CMS that's not from Texas A&M. So he's from Fermi National Accelerator Lab near Chicago. Don Lincoln, and he's our keynote speaker.
Wow.
So his talk is at 3 p.m., I believe, right, in the main, that big room. So like we invite everybody to please come to his lecture, and it's great to have Don here. So at this time, I would like us to thank the team at CERN for this very nice and interesting lecture. So thank you very much, guys.
Thanks for having us.
Thank you, Alexei.
It was our
Thank you,
pleasure.
everyone.
Have a nice day.
Thanks to our
Bye-bye.
audience. Thank you for coming. It's been a pleasure to show you some of what
For
we've been
the
working on,
great
and,
questions also.
Don't
Yeah.
be strangers, come next year. Thank you.
Ciao, ciao.
All right. Bye, guys.